This is Dr. Anita Rexlin Devraj, Associate Professor of Department of Physics, Amet University. Today I am going to explain about how to find the thickness of the paper using Airwedge. Hope you all have seen sodium vapor lamp and traveling microscope, everything in your physics laboratory. With the help of that, how we have to find the thickness of a thin wire or thin hair or hair-like structure or a thin paper. So obviously the main aim of Airwedge experiment is to find the thickness of a thin material. You might have some doubt like finding the thickness, we can use a scale. Obviously we can use for a thick materials, and if it is a thin material we can go by with the help of screw gauge, vernier caliper also we can find. With the help of those two experiments we can find the thickness as well. But depending upon the pressure what the person is giving when they are measuring the measurements, the error will be more when you are using screw gauge and vernier caliper to find the thickness. So that error will be reduced by finding the thickness with the help of Airwedge method. So that is the main advantage of Airwedge method. So obviously, as I told, the main aim is to find the thickness of thin hair-like structure or thin paper or a thin wire. That is our main aim here. And the apparatus required are thin strip of paper, one rubber band, two glass plates, one thin glass slab, and a monochromatic source of light. You know, monochromatic means it emits only one color. Okay, so that is a monochromatic light. Here for our case we are using sodium vapor lamp, and convex lens we are using, and traveling microscope as well. Before start doing the experiment, we have to form the Airwedge pattern. And how we can do that? So we need two glass plates, and that will be held together, and one end we have to put the rubber band to tighten it. Okay. On the other side, we put the piece of paper in between those two glass plates. So it will create a wedge shape, and in between those two glass plates air will be there. So now this is the Airwedge which we have created to do the experiment. Now you can see this is the experimental setup, and first we have to create an Airwedge as I explained in the previous one, and place a thin glass slab above the Airwedge so that will work as a partial mirror. Okay. Then place the monochromatic light, that is sodium vapor lamp, in front of this apparatus, and place the convex lens such that the sodium lamp, that is monochromatic lamp, is at its focus and giving us a parallel beam of light. Now place the traveling microscope above the 45-degree glass slab to see the interference. Now how it will be working, that we are going to see. So now switch on the lamp. It will take 5 or 6 minutes to brighten it. Okay. Once it got the bright light, then the light from the lamp travels through the glass plate and it gets refracted. Then the light passes through the Airwedge into the other glass plate. After the reflection from the bottom of the other glass plate, the light flows from the same route and then back up. Due to these refraction and reflection at the same time done by the light is out of phase with one that will be getting partially reflected from the top surface. So these lights in different phase causes interference and form fringes. I think you know what is interference. Interference needs two or more lights. Interference will be happening in lights as well as sound. Okay, and two or more lights traveling in the same path will be coinciding with each other in two ways. That is, both the crust will be falling on the same position, or both the trough will be falling on same, or sometimes crust and trough will be falling on same place, same time. Okay, if both the crust and trough will be falling on same phase means that is called constructive interference. During constructive interference you will be getting bright fringes, and the other case, that is one wave's crust and other wave trough will be falling on same time means that will be called as destructive interference. During destructive interference we will be getting dark fringes. Okay, so here the fringes are alternatively dark and bright based on the path difference as I explained. So the fringes are formed as the superposition occurs. Depending upon the path difference, the waves in different phases overlaps. So this is the Airwedge fringes, and the fringes will be formed like this. So first one, the blue color, what we have shown is the side view of the Airwedge, and the fringes will be shown in the second image, like the top view. Yellow color or the monochromatic source of light, that is the bright fringes, and the black lines are called as dark fringes. So alternatively, bright and dark fringes we will be getting as a pattern of this experiment. And we have to use some formula to find the thickness. So condition for maxima, what they have given is 2 mu x theta is equal to 2n minus 1 divided by lambda by 2, and condition for minima is 2 mu x theta is equal to n lambda. But our aim is to find the thickness. So by simplifying all these terms, we will be getting T as lambda L divided by 2 beta. So T is the thickness of the material what we are going to find. Like it might be a thin paper, butter paper, or it might be a thin wire, or it might be a hair. So that is called as a thickness of the material T, and which will be measured in meter. And lambda is the light source wavelength. That is, here we are using sodium vapor lamp 5896 or 5893, sometimes they are using. The unit will be in angstrom. That is, if you want to change it as SI unit, into 10 power minus 10 meters you have to put. And L is the length between the rubber band to the other end where you have placed the material like hair or thin paper. And beta is the fringe width that we are finding with the help of the tabulation. And 2 is the constant number, we know that. And this is the table. This is how we are observing the reading from the XY microscope or traveling microscope. We need to find for every fringes, and then have to record the main scale reading, vernier scale coincidence, and convert it as a vernier scale reading, and then total reading, then finally find beta reading. So you can take the mean of beta, and that will be applied into the formula. Finally we will be getting the answer as. So with the help of these readings in the given tabulation, we have found the length of the wire L is equal to 30 mm, and wavelength is lambda. Here we are using 5893 angstrom. Beta value will be 0.108 mm. Finally T will be found as 0.081 mm. So the thickness of the thin butter sheet here, what they have used is 0.081 mm. And now we have to write the result and conclusion. Finally, the thickness of the paper came out to be 0.081 mm, and we can see this is actually a very thin material. Okay, so the error is very less compared to the thickness we have found with the help of vernier caliper as well as screw gauge. And some precautionary actions we need to do when we are doing this experiment. The main three things are: glass plate should not be cracked, it should be very clear and clean, and no other dirt particles or liquid should be enter into the wedge. And the glass slab which reflects the light should be kept at 45-degree angle. So these are all the important things we have to consider, or these are all the precautionary measurement before doing the experiment we have to consider. Thank you.